Welcome to this video on natural selection. In this video, we will explore the fascinating concept of natural selection and how it shapes the evolution of species over time, and we'll show how this works through simulations. So whether you're a biology enthusiast or simply curious about the world around you, join us on this journey to uncover the secrets of natural selection. Natural selection is a fundamental process that drives the evolution of species over time. At its core, it depends on three key factors: variation, survival, and heredity. Variation refers to the differences that exist between individuals within a species. This variation can arise from genetic mutations, environmental factors, or a combination of both. Second, survival refers to the fact that not all individuals will survive and reproduce to pass on their genes to the next generation. Those individuals that are better adapted to their environment and are able to successfully compete for resources are more likely to survive and reproduce. This is also referred to as survival of the fittest. Third, heredity refers to the passing on of genetic traits from one generation to the next. Traits that provide an advantage for survival are more likely to be passed on to the future generations, leading to the gradual accumulation of beneficial traits over time. Together, these factors create the conditions for natural selection to operate, driving the evolution of species through the gradual accumulation of advantageous traits. In this video, we will explore these concepts in more detail and see how they apply in some simulations that we create. To help illustrate how natural selection works, let's take a look at an example involving two moths of different colors. If these moths were to mate and have offspring, there would likely be a range of colors among the offspring. Now suppose there is a predator in the area that can more easily spot the lighter colored moths. In that case, the lighter colored moths are more likely to get eaten, reducing their chances of reproducing and passing on their genes. Over time, the proportion of darker colored moths in the population would increase as they are better adapted to surviving in their environment. In this example, the color of moths is determined by genes that are passed down from their parents. When parents reproduce, their genes mix and their offspring inherit a unique combination of genes from each parent. This process is known as heredity and is a critical component of natural selection. Throughout this video, we will see this example of natural selection in action, helping to give you a deeper understanding of this essential process and its impact on the evolution of species. In these simulations, we will be using the peppered moth to show how natural selection works. The peppered moth is a species of moth found in England that became famous for its role in illustrating the process of natural selection. Prior to the Industrial Revolution, most peppered moths had a light coloration that blended in with the lichen-colored trees they lived on. However, as the pollution from factories darkened the trees with soot, a darker form of the moth became more prevalent since it was better camouflaged against the darkened tree bark. This change in frequency of the moth's coloration over time illustrates how natural selection can operate in response to environmental changes. Let's dive into a simulation to see how natural selection operates in the context of the famous peppered moth example. We will set up the simulation on a grid of cubes, where each cube represents the color of tree bark that a moth will settle on. Every day, the moths will land on a cube, and if they survive for 10 days, they will have a single offspring. It's important to note that the offspring won't necessarily be the same color as their parent. Instead, the color of offspring is determined by a normal distribution, with the mean being the color of the parent. Our predator in this simulation is a bird, which will fly over the grid of cubes where the moths have landed every day. The chance that the bird will notice a moth is determined by the color difference between the cube the moth is on and the color of the moth. If the bird notices the moth, it will have a 75% chance of eating it, giving an additional chance to the moth. This simulation will help us visualize how natural selection operates over time, as we watch the peppered moth population adapt to the changing environment around them. Here is a visual of how this will work. Each day, each moth will settle on a single cube. If you look carefully, you'll notice that 3 moths have settled along the flight path of the bird. After the moths have settled, each bird will start from the trees, make their way into the middle of the grid, and then back out again. As they fly over the grid, they will either notice or not notice the moths that are on them. Here you can see the percent chance that each moth will be seen based on its color versus the color of the cube it sits on. We will start with a population of completely random color moths. There will be 50 at the start. We'll run this simulation for 200 days initially as a break-in period. At that point, we can take another look at the moth population. After 200 days, we will start turning the grid slowly darker to simulate the darkening of the bark in the peppered moth example. 100 days after that, we will stop changing the color of the grid and let the moths adapt to the new color of the forest, and we'll take another look at the population. On the top of the screen, you can see a histogram of the population in real time as the simulation plays out. Let's take a look at some results. In this figure, the solid white line is the median color of all the moths. The green area surrounding the white line is the 80% confidence interval. That means that 80% of the moths are in this green area. You'll notice that it starts really wide, and that's because we chose moth colors randomly in the beginning. Finally, the dotted line is the average color of the trees. This starts out flat as we had a 200-day burn-in period. Then the trees start getting darker quickly. Finally, at day 300, the tree colors stop changing. What's important to notice here is that the moths generally hang out around the dotted line until day 200. Once that happens, they start diverging. The moths are definitely getting darker, but the trees are getting darker at a much faster rate. Once the tree colors settle at 300 days, the moths are still catching up. But if you'll notice, around 350 days to day 500, the moth color doesn't appear to change over this time. It seems to reach an equilibrium, a point where there isn't too much pressure on them to change color drastically. Let's take a look at another graph. On the x-axis is the color difference from the day the moths were born to the same day average tree color. So the farther to the right on this x-axis, the more the moth will stick out compared to the average tree color. On the y-axis is their age at death. So the higher up a dot, the longer that moth lived. Each moth in our simulation is represented by a single dot. Now you might start to see a trend in these data. There appear to be a lot of dots in the upper left and not so many in the upper right. Let's add in a linear trend line to see how this looks. As you can see, the trend line decreases as the average color difference increases. What this means is that moths tend to die earlier when their color is farther from the average tree color at birth. And this makes sense, it's the whole basis for natural selection. Without the pressure of tree color to camouflage the moths from the birds, our moths could be any color and it wouldn't matter. But this is only one simulation. Let's run a few more to see if this holds up. As you can see, there are many differences in these simulations. It even looks like a few moth populations went extinct before the 500 days were up. But one thing that sticks out to me in this graph is how a lot of moth populations plummeted after that 200-day mark. Let's show this data in another way with some summary statistics. In this figure, the white line shows the average number of moths in each simulation as the number of days progress throughout. The green area surrounding the line is the 80% confidence interval again. As we noted in the last figure, the number of moths decreases in the beginning and slowly builds up a population to just after the 200-day mark where the populations plummet. It takes them a little while, and some of the moth populations went extinct, but they do seem to be gaining back population as the days approach 500, with a strong increase right at the end. Let's add in some more simulations. The simulations we just looked at are the medium color change simulations. We also ran one where we didn't change the color of the trees at all. That's the no color change. Finally, we added a slow and fast color change scenario. As you can see, the number of moths vary widely over time based on the scenario that they're in. The no color change seems to grow constantly, while all the others have at least a little dip. The fast color change scenario had a drastic decrease in moth populations after the 200-day mark, but the populations never really recovered. It also looks like a fair amount of the populations may have gone extinct altogether. Let's take a closer look at that. Each of the green lines shows when one moth population went extinct completely, meaning they didn't last until the end of the scenario. As you can see, the lines slowly get more numerous as you go down. That's because the fast scenario had the most amount of extinctions, and the no color change had the least. This makes sense. When an environment goes through drastic changes, it's hard for the populations to keep up. Natural selection can take a long time, and not all populations will be able to adapt fast enough to survive. That's all for the simulations. Let's take a look at our original checklist. Our moth populations had variation in their color. This variation had an impact on whether the individual survived, as the moths that were more camouflaged to the trees survived longer. Finally, the color genes were passed on to offspring, showing heredity. That's all for this video. Feel free to subscribe if you'd like to see more content.